Hi, this is Ivan Martin from the Institute of Space Sciences in Barcelona, and here I'm going to be talking about the main project for my PhD on trying to apply machine learning methods to parameter estimation for massive black hole binaries. This is all in the context of the LISA data challenges, which I'll briefly explain in case anyone is unfamiliar with them. The LDC group periodically releases simulated LISA data consisting of injected gravitational wave sources and instrumental noise, and it is the task of the participants to analyze this data in any way they see fit and see how much science from the injected sources can be extracted out of it. This serves as a benchmark of sorts for the algorithms and incentivizes their development and their improvement as the released data gets more and more realistic. But it also requires an effort in development of waveform templates and instrumental simulators that will be similar to the real thing once it launches. The end goal is to be sure that we can analyze the data once the mission is flying, and to have a common toolkit for all the science that can be extracted. Participation is open, so if you're interested in LISA data analysis, you can go to the website and join us. One of the main sources we expect to see in LISA are massive black hole binaries, binary coalescences consisting of pairs of supermassive black holes, of masses of the order of 10 to the 5 to 10 to the 7 solar masses. These are expected to merge within the LISA frequency band, and thanks to the high masses, they will be having very high signal-to-noise ratios, up to the order of 1000. The models that describe them, however, have quite a few parameters, and some, such as the sky location, do present degeneracies and multimodalities. As a waveform model, we're using IMR phenom-D, which is the same that has been used to produce all the LDCs released up until now. Here's a list of the parameters that need to be estimated. They include the masses and spins of each component black hole, the location in the sky of the source and our distance to it, the time when the coalescence happens and the phase of the waveform at set time, the angles of inclinations of the orbital plane, and of each of the spins relative to set plane. Now I will talk about our goals. We are starting with some data coming from the LDC, and the dream scenario would be that we somehow treat it, feed it into some trained neural network, and that would output a vector phi that somehow describes a posterior distribution, that is, the probability distribution that the waveform parameters take any combination of values given the data that we fed the network. Of course, this is easier said than done, but it is in this direction that we want to go. Traditional data analysis methods, such as Markov-Chain Monte Carlo or nested sampling, require computing a likelihood function, which generally makes some assumptions about the instrumental noise and requires forward simulations for every sample we make. We expect that going this way will require lots of simulations and number crunching during the training, but once that is done, if the network is trained properly, evaluating our data will be orders of magnitude faster and cheaper as we are skipping computing the likelihood altogether. So it's mainly a matter of long-term amortization of compute power. Okay, so for the training we first need a lot of data. This means a way to mass produce LDC-like datasets is crucial for us. Most of our work up until now has consisted of building data generation pipelines. The idea is simple. We start from a specific prior distribution for all the parameters, which we randomly sample as many times as we want to build up a catalog of waveform parameters. Each of these are then fed into IMR phenom-D and projected through LISA, so we end up with a TDI X, Y, and Z time series waveform channels. Then comes some data preprocessing, which transforms this data into a form that is suitable for neural networks and which we have purposefully left very modular. This includes things such as adding in noise, wetting our data, and various transformations. It can also include things like Fourier or wavelet transforms, which are implemented but not currently used. We've essentially built two pipelines like this. The first one is very fast, taking advantage of an assumption of stationary Gaussian noise to first whiten our waveform data according to a theoretical noise PSD. Then very quickly injecting noise following a standard normal distribution. Of course, that assumption isn't always very accurate, so we also built a slower, more realistic pipeline that runs the LISA node instrument simulator for the noise. This pipeline is heavily based on the one used to generate spreads, which is one of the LDCs, but with some retooling and removing the instrumental glitch generation part for now. Anyway, now that we have the ability to generate data, by default in the LDC we're simulating a year of data with one sample every 5 seconds, which with 3 channels amounts to almost 19 million numbers per simulation. This is completely unfeasible for neural networks, so the next important thing we need to do is to compress this data to more manageable numbers. We'll start doing so by conventional methods. The first thing we can do is to sample our data less often. Downsampling our data in this way implies that we'll be reducing the Nyquist frequency, or the highest frequency that we'll be sensitive to in the data. But as long as our gravitational wave signals have a frequency lower than this Nyquist frequency, we should be free to downsample. For compact binary coalescences, the gravitational wave frequency monotonically increases during the inspiral, up to a maximum during the merge. This merger frequency is actually inversely proportional to the total mass of the system, so the highest frequency we can expect will be with the lowest masses in our prior. Here to the right in blue is the frequency domain simulation of the waveform with these lowest masses, superimposed with some instrumental noise. The vertical lines represent the Nyquist frequency if we were to downsample up to certain values. From this, we can see that an appropriate value for the cadence is 15 seconds, allowing us to compress by a factor of 3 basically for free. The next obvious thing that we can do is to reduce the observation time. A year is a lot of time, and most of it will be either way before the merger or after it, when there is not much information. So we should be able to crop around the merge without too many problems. In terms of timescales, the ring-down decay happens much faster than the inspiral chirp, so we need to have more time before the merge than after it. It is for that reason that we have decided on an 80-20 split. Next, we need to find out how much we can crop our waveform by without it being too much. As a metric for this, we use the signal-to-noise ratio. How much information is in the inspiral relative to the merger has a much more complicated dependence on the parameters than something like the merger frequency. So for a dataset involving 2000 simulations, we compute the SNR and see how that number evolves as we keep cropping more and more. This is shown on the figure to the left. The shaded region are the contours of the SNR as we crop more and more of the inspiral from right to left. Some examples from the 2000 are shown in the form of the colored curves. For very short times, we get that sometimes the SNR increases, which is strange, but we attribute to some numerical error at these short times. Anyway, we see that if we cut to 1 day before the merge, even in the worst case scenario from our dataset, we still keep over 99% of the SNR, so we decided that it would be appropriate given the massive compression that it means. Finally, another traditional compression trick. Our data is in 3 TDI channels, X, Y, and Z, but we can convert it to A, E, and T with simple linear combinations. But the T channel has no gravitational wave information and the approximation that we are at low frequencies, so it should be safe to discard it and just use the A and D channel. With these 3 techniques, we end up with 2 channels of 7000 data points each. This is compressing our data by a factor of over 1300 with some 1% of loss of gravitational wave information in the worst of cases, but our data is now much more manageable from a machine learning standpoint. So now as a sanity check, we decided to get some basic point estimates of our data using a multi-layer perceptron. This is a fully connected neural network with a few hidden layers. Data without any noise was fed into it, and we trained it so that the single neuron in its final layer would give us the chirp mass of the system, using the standard mean squared error loss. We used a small dataset of 20,000 gravitational wave signals and let it train for about 25 minutes, and the result you can see in the figure to the left. The x-axis is the true chirp mass of the data, while the y-axis is what the neural network predicts, so the correct values should lie on the diagonal. You can see that while it is not exactly great, it still did learn quite a bit from the training data, and the validation and test data also more or less follow the trend, letting us know that the neural network is indeed learning something, which is a very good sign considering the small dataset and the very short training time. Okay, so now to wrap things up. For this multi-layer perceptron, we have made several simplifications, but given that we have the tools, now we should be able to creatively lift them. But simple point estimates are not really our goal, and indeed we are also exploring how to properly learn in the Bayesian way, and looking at methods to learn either the posterior or the likelihood function. This includes methods such as mixture density networks, masked autoregressive models for density estimation, normalizing flows, and many others that exist in the literature. We're also looking at ways to compress our data even further, since having less things to train is likely going to help our neural networks converge faster and avoid overfitting. We were very recently given the suggestion to use the singular value decomposition as a way to compress our data, or at least as a linear initialization for our neural network that compresses our data. Some time ago, we explored using information maximizing neural networks to produce non-physical summaries that maximize the Fisher information matrix and a fiducial value of the parameters, but while it seemed promising, without a way to estimate the parameters, we had no easy way to interpret things, but now it would also be a good time to revisit that idea. And with that, I'm done. If you are interested in this work and have any questions, suggestions, or ideas, please let me know by sending me an email. Any comments are also greatly welcome. Enjoy the rest of the symposium. Bye.